Alright guys, this is going to be a video that goes with number 4 on 8.4, the challenging one. We do have a handful of these throughout this chapter, so let's practice it here real quick. So here in this particular setup, I have a spinning wheel up top up here, like a spinning cylinder. So in the middle of it right here would be like a bar. So you can kind of think, let's think, oh, I got you a perfect scenario, actually a hilarious scenario. Toilet paper. Toilet paper coming off the side. This thing is spinning, and there is toilet paper hanging down here. This is essentially what we're looking at, with the only difference being I've got apparently something hanging from the bottom of the toilet paper. Based on my life right now, it's a monster truck. All right, so definitely don't take into consideration the masses that I gave both of those for being toilet paper or a monster truck. But let's do a force diagram here real quick. All right, now when you look at this guy right here, this guy is going to go downwards, and it's not going to rotate, which tells me immediately I don't really need to do an extended force diagram. I just need to do a regular force diagram since it is not rotating. So let's start with the easy one. There is definitely force gravity down. Now, since I'm going to be dealing with two force gravities in this particular scenario, having a second object, I'm going to call that force gravity hanging. Next, there is definitely a force pulling up. Now, let's talk about this for a brief second. If the object over here was entirely by itself, oops, that was an accident. Let's try that again. Nope, let's try that. I don't know what it's doing. Maybe? Maybe. There we go. Okay, copy. Paste, my apologies. Okay, if the object was entirely by itself under just the force of gravity, we know that it would accelerate at g at 9.8. Okay, what a lot of people try to make the assumption on this problem is they try to say, oh, force gravity and force tension are equal to each other. We also know that's not true due to the fact that they are equal to each other. This thing's not going to accelerate at all in this particular case. So I know it's going to accelerate down, but I know it's not going to be 9.8, which tells me that force tension is just smaller than force gravity hanging. Okay? And that's all the forces that's acting on that. Now this roll or cylinder right up here is definitely going to have, definitely going to be rotating. So that tells me that I need to do an extended force diagram on it. So what is my extended force diagram? Well, for starters, over here on the side, I would have force tension pulling down on that rope. These two guys right here are in fact the third order pair of each other, so I know they are equal to one another. Oops. Okay. Next, the thing's going to have force of gravity, so this would be force of gravity. We'll call that cylinder. Go with that guy right there. And since there's some type of probably post right in the middle of that, there's going to be some type of force normal. And that should be, just using basic forces, those two are pointing down, so this should be equal to that right there. And there's my force diagrams. Now, the purpose of this could be a few things. I'm just going to make it easy on us right now and say we're looking for the acceleration of this particular system. And I say this particular system because this guy is going to accelerate, and the outside part of this is also going to accelerate. I say outside because we'll talk about that in just a minute. So the easiest place to start by looking at this would be looking at the sum of forces on this right here. So I'm going to sum the forces in the y. And actually, before we get too much further, there is one thing that we actually did earlier this year that really, really helps us when dealing with multiple objects. And that is, I can get really weird with positive and negative here. So what we do is we say, I'm just going to establish a direction for positive. And usually the easiest thing to do is the way it's going is going to be positive. Now notice that is going to flip the signs that we're used to right here. And it is also going to flip the direction of signs on torque that we deal with right here. All right, so let's go back to summing the forces now that we've done that. Now that we've just established down is positive, that would mean positive force gravity hanging minus force tension is equal to mass hanging, because that's the thing accelerating, times acceleration. And sadly, if you look at this equation, we could see, well, we could calculate that. That's just m times g. We already know that, but unfortunately we don't know that one, and we don't know that one, which means we have two unknowns. So we got to go somewhere to find those exact same two unknowns. Where are we going to go? Right up here. Now I'm not going to sum the forces on that because you already know how that's going to result. We know that's going to not accelerate at all. as we do know it is going to be rotating, we are going to sum the torques on that guy up there, and that should equal its moment of inertia times angular acceleration. Now, when you look at the fulcrum has to be placed at the center because that's the spot not rotating. So nice thing that works out here is even though there are 3 forces acting on this particular object, there are not 3 torques. There's actually only 1 torque. And that is caused by this force tension at that lever arm right there. Notice that lever arm is actually nicely radius and the angle is nicely 90 degrees, but let's go ahead and fill this guy out. Sum of torques. That force tension would usually be a negative torque, but because of what we did earlier, that is a positive torque tension, and that's the only torque. Moment of inertia, we talked about this on the chart. You just find the one that goes with this particular shape. In this case, it is a cylinder spinning about its center, so that is 1/2 mass of cylinder times radius squared times angular acceleration. Okay, and if I fill out this left side right over here, that's going to be lever arm times force tension times sine theta. And a couple nice things cancel out. 1, the angle is, as we already said, 90 degrees, so that's 1. 1 of this right here, is the lever arm. But as we've already stated, the lever arm is from the fulcrum to where the force is applied. And you'll notice nicely from the picture that lever arm, being radius, is in fact going to cancel out with one of those radiuses right over there. Next, you might notice as you look at this equation that we know this guy, and we don't know radius actually yet, and we don't know force tension, and we don't know alpha or angular acceleration. Now, to get 2 equations, 2 unknowns, we need to have the exact same 2 unknowns. So we have force tension and acceleration up here, and we have force tension here, but we don't have acceleration. Luckily for us, there's a nice relationship between acceleration and angular acceleration that we discussed last chapter, and that is regular acceleration is equal to angular acceleration in radians per second times r. So I am just going to solve. This is going to be alpha is equal to a over r, doing the algebra of that, and substitute that right in there. And this gives us force tension equals 1/2 mass cylinder times radius times acceleration over radius. And so actually nicely our last radius cancels and we don't need to care about what the radius is. So now, if I went over here to the side, here are my 2 equations. This guy, I'm going to replace this equation while we're talking about it, is mass of hanging times G minus force tension is equal to mass of hanging times A. And then this equation here is force of tension is equal to 1/2 mass of spinning, mass of cylinder rather, times A. And I got 2 equations, 2 unknowns, so I can either use substitution or elimination. Now, almost always people use substitution because that's just what they get used to. But elimination is actually the easier bet here, and I'll show you how it's easier and why it's easier. For starters, elimination, if you remember, hey, if I get an equal sign, we don't know what the number is, but that's something like 10, and that's something like 10, and this equal sign is this is something like 2, and this is something like 2, meaning both sides are obviously equal. Now, what that means is that I can then kind of take this side and either subtract them or add them and do the same thing over here, and they should still be equal. 10 minus 2 is 8 on both sides, or 10 plus 2 is still 12 on both sides. But that means if I add this guy to this guy, it should be equal to this guy and this guy, and the nice thing that happens is notice that these are equal and opposite, so they will cancel. And the reason why that's going to work out a lot of times in physics is the reason why these guys are equal and opposites. And that's because that's a 3rd order pair. So anytime that happens with 2 objects and you're dealing with a 3rd order pair, this is regularly going to come up, and so they regularly cancel. So this is all that's left on the left. The right should be mass hanging times A. This 1/2 mass cylinder times A. We're going to go ahead and I'm going to digitally cheat here. Factor out the acceleration. Divide that all underneath. Mass of hanging times G over mass of hanging plus 1/2 mass of cylinder, and that's our acceleration. So that would be 5 kilograms times g over 5 kilograms plus 1/2 of 3 kilograms. And I get 7 something. That's on my calculator second here. 5 times 9.8 divided by 5 plus 1.5, and we get 7.54. And you can be sure that that is in fact the right answer, because you will notice that that amount of acceleration is between what we talked about earlier. It is not 9.8, which is exactly what you would have if that was the only one, but it is definitely not 0 either, because this is not balanced. That is definitely less than force gravity. Other things that would be asked on this problem, we've done the bulk of the work here, so I'm not going to do any more, but other things that are asked on this, going to be asked on this problem is like, hey, what is the force tension in this case? Well, if you know acceleration, it's just like 2 equations, 2 unknowns. All I would do here is take that acceleration, plug it in there, or plug it in there, and solve for your other variable, and that would tell you how much force tension is. Also, right here in this step, we went from angular acceleration to acceleration by substituting. A lot of times the opposite might happen, where they want to know angular acceleration. So what you can do is just use that guy and substitute it in there so that you can get angular acceleration on the very end. All right, there you go.